So our next sort of external perspective talk, shall we say, is going to be on AFLOW, which I made extensive use of some of their online tools as a PhD student. That was like the quickest way to get some of the like structure file formats I was working with converted. There's a nice online tool you can like paste into it and get converters and things like that. And they've got a bunch of great databases and online things to parse through that I'm sure Simon will tell us about. But anyway, I'm delighted to introduce Simon Divilov from Duke, who will tell us about AFLOW. Thank you very much. Take it away.
Great, thank you so much, Rachel. So just, AFLOW is probably not as well known as the, let's say, maybe other databases, even though it is one of the first. So I'm just curious how many have heard or at least used AFLOW or like went on the website. Okay, good. So about maybe 40. Let me introduce the team. So we have at the helm, we have Stefano Corrolo. He's, he has sort of the, let's say, the projects, and then he designates the projects to us. So the most senior people are Hagen Eckert and myself. And we have a few new postdocs and actually recently a graduate student. And we kind of, we get tasks when we try to distribute the tasks, and I will talk about that as well. Mike Mel, he's a research professor. He does a lot of AFLOW prototyping. If you guys don't know what that is, I will discuss that as well. And then outside of Duke, we have David Hicks. He's at Lyft. He does a lot of, or he did a lot of the symmetry stuff that's in AFLOW. We have Rico Friedrich in Germany, in Dresden, and he does, he kind of does the 2D equivalent of AFLOW. So he has his own database for 2D materials. I think maybe more focus on biochemistry. And then our most recent collaborator is Rico Calzolari. He's from CNR Nano in Italy. And he's helping us with a lot of more exotic properties of materials, specifically related to plasmonics. So AFLOW is kind of started because materials have very interesting and very diverse properties, right? So you can have, you can have thermal barrier coatings, which are very useful in the energy and aerospace industry. There are super hard materials and wear resistant materials that is important in machining. So, for example, like stir-weld welding, they want really, really super hard materials and materials that can also withstand high temperatures. Then there's also materials for biological applications. So these are like your metallic glasses. If you have any metallic implants, they really will use those type of materials. Then there's solid state, so batteries. A lot of people study batteries. Solar energy, right? So you have your photovoltaics, then the batteries, and what else I have on the list is superconductors. Although that is maybe more of an aside because it's not very straightforward to study that directly from typical first principles like DFT. And so to study all these materials, or at least predict these properties, we have a huge, selection of elements that we can choose from. And, for binary, I just took here the 70, let's say, most common elements. And as you see, as you combine more and more elements, the number of combinations that you can have just explodes. And that's just the combination of elements. That is not taking into account also the different crystal structures that can exist given the same element. Of course, a lot of them might not be thermodynamically stable, but a priori you would not know this information. So you're looking at the order of 10 to the 177 possibilities. So kind of this is where AFLOW, this was the, let's say, the motivation for AFLOW to be created. And typically what we do is we start from some experimental structures or some experimental database, like the ICSD, and we take a structure, so typically they use CIF files. I'm sure you guys are familiar with that. In principle, AFLOW can use a whole bunch of files, file types. And the idea is that you pass it into AFLOW, it will create a specific AFLOW file, and there it will automate your quantum chemistry calculations, so density functions, typically. And I'm gonna talk about this in more detail. And then the idea is that once you do all these calculations, you create a database, you store the calculations, similar to what Jason was talking about for AIDA, and that this database is searchable, and that's pretty much what aflow.org is, at least part of what's available there. And then ultimately, the output of whatever you're looking for, that you aggregate the data and you create some sort of machine learning model for the properties and the applications that you choose to do. So, as people said before, they kind of are familiar with the AFLOW website. Here you can go on the aflow.org. You can type in an ICSD number, or you can search just elements. So you can put in copper gold, and it will produce all the copper golds, let's say, in the system. And it has visualizations, it has information about band structures and density of states, this type of. But that is, of course, what the user sees. So what is actually happening before we can get to that stage? So the way you can kind of think about it is you have your DFT code, some software, whether you're using VASP, Quantum Espresso, or maybe Vine2K, right? And AFLOW really will try to control what inputs you put into your code. So what we're going to do is we're going to start with what is called an AFLOW in file. And this technically is not, you don't build this file from scratch. So typically you have let's say a structure file, like a CIF file, or maybe already from VASP you have a POSCAR file. And what you do is you feed this file to AFLOW that will then generate you this AFLOW in. And inside this AFLOW in, it will have information about, of course, the structure itself, but also anything that you want to add on top of that. For example, if you want to do phone line calculations, that will be inside the AFLOW file. So kind of everything there it's a text file, and everything there is you can have different pieces. So the way you would work with it is you would, let's say, uncomment a piece that's related to, if you're doing this by hand, let's say you would uncomment a piece of the AFLOW file that's related to, let's say, the elastic calculations, or if you want to do, let's say, free energy calculations, you would uncomment. Of course, you can also do this directly from the command line interface, and that's typically how we do it. Okay, but let's say you produce this file, you don't do anything fancy, and then what this file tells you is, okay, you have a structure, and I might have to do one or many DFT calculations, right? So, as the case for elastic calculations, you would have to do multiple DFT calculations. And a lot of times what happens, I mean, maybe now this doesn't happen as often as it used to, you run into errors, whether the errors are related to your K-grid, whether they're related to your other convergence parameters like the energy cutoff, maybe your kinetic energy cutoff, your basis set. So you have a lot of these issues that arise, and what AFLOW will do is it will detect them, kill the DFT calculation, so as to not use additional resources and restart the calculation by fixing whatever convergence parameters or input parameters that are, let's say, correct or insufficient. Now, and once you do that, once the calculation is complete, then also AFLOW goes and calculates all these properties. It stores these properties then in a database. So kind of like AIDA, there's two parts. You have all your files that are compressed and zipped, and then it creates a JSON file, and that's actually what when you're how to say searching on the AFLOW website, that's actually what you're searching. You're searching through the JSON files. Also, you do have access to some of the let's say raw files if you need them. And the call, what we use is called AFLOW. So this is kind of the API. So we have a bunch of, you can give it a bunch of things that you're interested. Let's say, of course, this is not a presentation about AFLOW, but you would give it, let's say, information about, let's say you want a band gap between 2eV to 3eV, or if you want all structures that have chromium in them, for example. So you can build this type of query, and then it will go and give you all the structures. And of course, this is something you can, if you're using AFLOW, let's say privately, you can also build this type of database yourself. And there's a bunch of, let's say, keywords that you can use to get that you want, ideally in a single query. Okay, so this is kind of what AFLOW is and what it can do. So now let me talk about a little bit of facts. So development in AFLOW started in 2004 by Stefano. So that was 20 years in development. It's written in C++, everything, and it was it started with C++ 98 the standard. There's a huge amount of lines of code. So and that's that's kind of you might think it's a good thing, but it's actually it's a sour point, because it's kind of hard to, especially if you're someone new coming into AFLOW, figuring out where everything is. And especially if you think about maybe like Python or Julia, you can just Google. I don't know, you don't know how to use lists or something like that. You can just Google lists, right? In AFLOW, because every like type that we have, I mean, other than maybe doubles and ints or something, strings, they're custom. You can't really Google this information, and so there has been a huge entry barrier into, let's say, being a developer in AFLOW, which is part of why the reason we're kind of a very small group. We do only utilize basic external libraries. That's just simply because we want to keep, if we do any sort of updates, or there are updates that are done by external developers, we don't want anything to break. So this also means that if you want to introduce some sort of something, use something externally, you have to figure out how to actually pull that code into AFLOW. And of course, there's pros and cons to that. And we interface with many ab initio softwares. And over the years, a lot of modules, quote unquote, which are just C++ files, have been created that you can call within AFLOW that do what you want. So again, like if you want to do related to elasticity, maybe convex hull, symmetry, and so you can call these separately. But this is why the code is so big, because everything is, let's say, I mean, in separate files, but it's all in one. You have this all-in-one kind of software. So I'm going to start talking about things that we kind of learned over the years. I mean, specifically more, things that we learned more recently. But before we even discuss the code, I kind of want to explain that AFLOW has its own calculation standard. So when you create this AFLOW file and you do the calculation, it's going to do it's going to take certain steps before it's not just going to take your, let's say, structure and then perform some sort of, let's say, DFT calculation. So what I mean by that is we start with, let's say you give it a structure, right? So you have this AFLOW in. You're going to be doing an ionic relaxation that we call relax 1. And there are, of course, it has there are specific cutoffs that are set by AFLOW, specific, let's say, K grids. So what we use is we use this parameter. It's the number of K points per reciprocal atom. And what this means is that, if you have a very large, I'm sure people know, if you have a very large supercell, you want to use a lot less K. Well, you need a lot less K points, right? Because you don't really need to make a lot of periodic images. Then after we'll let that run with whatever ab initio code you have. We do a relax 2. So that is, you can think about like an annealing step, right? So when you start your simulation, you assume that the wave functions are, let's say, as neutral atoms, and then, right, then you have your relaxation, and then you minimize the energy. With relax 2, you again restart with the wave functions being in the positions or in the, let's say, the state of the neutral atom. And then you again do ionic relaxation. In principle, you can keep doing this, but we found after, empirically after relax 2, so after doing this twice, you don't really get too much of a decrease in the total energy. And once you're finished with that, then what we do is we call what's called a static calculation. So this is a single point calculation where we crank up the convergence parameters about, let's say, 30% higher than what was used for the relaxation part. And once you're done with that, then we can access all the, let's say, the features that you then want to measure or you want to extract. So we have bands, again, elastic properties, free energy, right? One thing about the bands is, I'm sure you know that there's a standard for how you move along the Brimont zone, and this was actually created first in AFLOW, right? And I think it's AAC uses it and everyone else. And then, of course, something I didn't also should talk about is pseudopotentials. So we have a list of all the pseudopotentials. So when we say we're using the silicon pseudopotential, we're using a very specific silicon pseudopotential. So everything is, let's say, reproducible. So you can go back, you should be able to use exactly the same thing that we're doing and get the same answer. The other thing that we have is we have a nomenclature for materials. So here I have an example of beta selenium dioxide, and so the string on the right is how we would represent it in AFLOW. So let me kind of go over each part. And so the first part is that this is a AB2, right? Let's say, so how the atoms are. So you have so there are 2 A atoms and 1 B atom. Here it's A to B because we always put everything in alphabetical order. So put all the elements in alphabetical order. That's why it's A to B. Then you have your Pearson symbol. So this is kind of a bird's eye view of what your crystal structure is. It's not, you still need to, after this, give the space root because the Pearson symbol is not unique enough. And then after that, you have your Wyckoff positions. So the Wyckoff, let's say, this is how many invariant points you have at for example, at the site. So for the oxygen, and then you have your invariant points for the B atoms, in this case, the selenium. And then there's this tag dash O2 or 002, sorry. So this is AFLOW. This is an internal AFLOW index. In principle, this is not important for the user, because think about it like this: if I gave you all of this so far, you still have to specify the lattice parameters, right? That is not really, that is not anywhere represented here. And so if you just gave the string, you would also have to provide the lattice parameters. What the 002 index does is it basically fixes the lattice parameters to some sort of values that we have pre-chosen that we found useful for us. And of course, you can use those or you can set your own. Okay, now the next things I'm going to talk about, and I can move through over them quickly because I didn't know also the level of of everyone here, and believe it or not, a lot of things were not, again, because this started in 2004, a lot of these things we did not have for a good chunk of the development cycle. So the first thing is, version control. This is like, almost like you would be shocked to know that when AFLOW started, we didn't have version control. We're talking like probably for the first, I would think almost 10 years there was no version. So once we got version control, this is like, and even if you're a solo developer, version control is great, right? There's you can just always go back, always have your information on the cloud, especially if you're using one of these services. The other thing is, I don't know how applicable this is to Julia users, but is to use an IDE. So I personally don't use an IDE, but what we found was that when we're getting new students or postdocs coming in, they struggled a lot, especially with C++. And so using again, I'm not affiliated with any of these, with JetBrains or anything like that. This just happens to be what a lot of what my group uses for an IDE, and they tell me good things about it. So, and I know they also have a plugin for Julia. Maybe there are, you guys know, maybe there are better IDEs for Julia specifically.
The officially recommended one is VS Code, but
VS Code, okay.
You can get it set up in a lot of IDEs for sure.
Okay, yeah, okay. So, but yes. So what I found is telling any incoming postdocs or students to get an IDE, because it makes their life a lot simpler, especially when you have a code like AFLOW where there's like hundreds of thousands of lines. And then this is related again to quality control. We have kind of now we have a quality control like procedure or standard. So so in our code we have a single branch, which we call staging, and the way we would create a pull request that we want to merge any sort of changes. We typically assign tasks to members. So here, well, this would be related to, let's say, if you created an issue. This is on GitHub, but with GitLab, there's and other quality control, let's say, websites. You have something very similar, and typically we need at least one person approving the code, the modification. So this way, we make sure that the code enters is actually functioning. And I'm going to talk about even other things that we do. And then, of course, we also want you to have there's some sort of, coding standards that you would have to abide by, including a big one that we've pushed for is documentation. Okay, so some other thing is know your quote-unquote target audience or your hardware. So we use a lot of stuff from the Department of Defense. We use their supercomputers. So for each supercomputer, we have a slightly different modification to our let's say workflow or our let's say runtime when we run our DFT code. So this is controlled by a bunch of flags here. I'm showing you part of the code, but just let's say the relevant part. Then we also have to talk about installation. So I know that Julia, right, it's kind of tricky, right, if you're using, well, we just seen yesterday, right, if you're using 1.10 and then if you used 1.11, I mean, maybe that was a very specific example where things were, things were becoming problematic. So with AFLOW, likewise, we have this next AFLOW tool. It's basically a very big bash script that you can run on Mac OS, on Windows and Linux, and it will set up AFLOW for you. Because what we've noticed over the years is that people had trouble compiling everything, even though in principle there's no external libraries that AFLOW needs. And most recently we actually switched to CMake, and this is like really easy. So now it's just you do CMake -- reset release set, and then you're kind of ready. So we try to make it as simple as possible for the user to actually install our software. And this is important also for us because when we run on so many different clusters, they're not all exactly the same, and this makes our life a lot easier. Another thing. So now we're going to talk about the C++ standard. So this is the C++ 98 standard. So this function it outputs the files in a directory. Okay. And so you have to use. And so in C++ 98, the way to do this, you have to use a lot of C functions. You have to use a few C functions. You had to kind of access certain, let's say, parameters of a file, right? So it was not very straightforward. And so one thing is when we see something like this, is okay. This function works, which is fine. But the problem is to someone coming in, they're more used to a more modern standard. We want to also modernize the standard, refactor that code. So here, this is written, the same function written in C++ 17. So now the only thing is you kind of have a single for loop over this output of what's called a directory iterator. And so another example would be that, in C++, the C++ 98 standard, you cannot create functions. So you could not pass a function into a function, right? So in Python, Julia, you can, there's no problem doing that. Here, this is a function that finds the zero using Brent's method. And this would not be possible in earlier versions. And as AFLOW moved more from just simply starting calculations to starting like DFD calculations to actually doing a lot more processing, we realized that this is something that we had to switch to if we want to keep using AFLOW. Another big thing is documentation. So, usually, the function would be, this is again the same directory ls function. So here it's just, what the function does is of course written in the comments. This gives you, the contents of the directory. But one thing we found very useful is switching to Doxygen. And here you kind of can tell what a function is, what the parameters are, information about the parameters, and we also have who modified the function and any notes. And I don't know if people really, do you guys use Doxygen or for documentation, or how do you guys do it?
In Julia packages, there's a package called documenter.jl that can then just build stuff and then talk to GitHub pages. I know, so not a lot of people use that. I don't know if other package developers have other things. That's the only thing I've done for Julia packages, but I know there are things that other people do.
Okay.
Yeah.
Yeah, so likewise, the Doxygen is very similar. It will make you web pages, and then the way these web pages are searchable, and you can again see this information about the authors, what the parameters are, any important nodes. So this is again important if we have to kind of go back and figure out, okay, if the function worked and it stopped working, what exactly happened. Big thing is also as AFLOW is doing things that are more computationally intensive, we needed parallelization. So this is parallelizing over in C++, you parallelize over the threads. So we had to create these templates. So template is kind of a very, let's say, a very general function. I don't know how to kind of describe it. And here we're able to give it the, let's say, the number of threads, what type of function it is. It's of course not as easy to use maybe as multiprocessing in Python, because you have to also create the let's say the multi-thread function itself, because this is just a template. This is something that that you would feed your multi-thread function. So I talked about error catching, right? So that's what the big thing of AFLOW, and there's quite a lot of errors. So over the years, we've kind of compiled all the errors in VASP. Maybe some of them don't really exist anymore. I'm not entirely sure, but you know, again, for backwards compatibility, if you're using an older version of VASP, you can still be confident that AFLOW will catch the error if it's gonna come up. And the other important thing is that we've started doing is that yes, you'll be surprised there was not an AFLOW before, was unit testing. So one thing we've realized is that kind of, especially as a user introduces new things into the code, if the functions are kind of complex, or if they use multiple parts or different parts of the AFLOW code, you want to make sure that everything is still working, right? Because there's so many lines of code, it's very easy to touch one little thing in one part of the code that will break another. And what we did is with our unit test is, of course, it's staggered. So if you want to only, so this screenshot I'm showing you is the unit test that's only associated with matrices. So we have a custom in AFLOW, we have a custom matrix class called S matrix. And for vectors, we have a custom class called X vector. So if you're doing something with matrices, you don't have to run all the unit tests. You can just run the one with X matrix. Of course, during the when you push to your changes to GitHub, we run on our own local server. We'll run all the tests just to make sure everything is properly working. And one thing we've realized is that the test can be quite exhaustive. Here we're looking. So this is a K-path test. So we looked at the K-path that we generate for VASP for all these different crystal structures is correct. And this is just kind of a for loop, right? So you won't run this every time, because probably in this case, you probably never run this, because you have to write this function once and then you're set, right? But the idea is that every time we push any changes, this part of the code gets run, just so we have a, let's say, peace of mind. And another thing is that we can also do unit testing externally. This is with CMake. So CMake, you can create unit tests as well, or at least which are basically, you call your program with different parameters, and you look at the output, and then you see if the output matches the output that you have stored. So we also now implemented all our, let's say, tests that were done in the bash, using bash scripts into CMake, and that's been really helpful to find bugs, which we found there was actually quite a lot, and that simply were not caught because all this framework was not in place. So the other thing, maybe this doesn't really apply to Julia users, so I will go through it quite quickly. This is using system calls. So if you notice here, we're using a lot of So here we're using this. This is for zipping, and we're using XZ or maybe bzip, depending on what input parameters you gave to AFLOW, or regular zip. But the problem is that you can't really do this using multi-threading. So you have to create locks or mutex objects, right? And it's also very slow. So we spent a lot of effort and energy to remove these type of system calls, even if it actually made the code longer. So here, I will show the new way of doing it. Here we're using libc, and you see actually the code got quite long. It just looks shorter because part of this code was put into just one for loop. And you have this more, let's say, you have to define these type of functions, or the variables in the beginning. So it's more, let's say, complicated, but then the code is so much faster because now we can just avoid system calls. And another big thing that we started doing, and this is important, as machine learning got more prevalent, is creating machine readable output. So again, I think I told you that the AFLOW, every database entry is already a JSON file, which is machine readable. But for example, we had this part of the code that would create these plain text files that had basically the atomic positions, the stress, and the energy, so the ionic steps. And what we found is that while it can be used, it's really hard when you have collaborations or you're just even working yourself and trying to read this data, because you have to create a reader for this. And maybe you're working in Python, you have to create a reader in Python. If you're working in C++, you have to create a reader in C++. If you're working in Julia, you would have to create a reader in Julia. So we switched to, again, JSON. We found JSON to be kind of the best because you can always make it also human readable, right? As opposed to, of course, you can use maybe other formats that are highly compressed, like HDF5. But what we found for us that storage is kind of cheap, so JSON works very well, and now you can use whatever you can access this information, read this information with whatever code you want, real language you want. Okay, so now let me briefly discuss the the successes with AFLOW, or how now AFLOW is used in the real world. So one big thing is we came up with this descriptor. So this descriptor basically can tell you we study a lot of high entropy systems. So high entropy systems mean that you have a system with many elements. And in this case, we were studying high entropy ceramics. So the way we studied, of course, high entropy ceramics is we do high throughput. So we have an element list of different metals, and we're looking, let's say, at carbides, and so we populate the. So we're looking at. So it's a rock salt structure. Maybe I should have had the unit cell here, but it's a rock salt structure. So you have carbon on, let's say, on one side, and on the other side you have your metal. And the way you study this is you generate all the possible combinations, right? And then you can look at the energy distribution of all your high entropy ceramics. And then from there we were able to develop a script. The reason I just bring this up because the amount of data that we had to, let's say, generate and calculate, I think it took like 3 years in total. So this was actually it started even before me, just generating data. But this just shows why I want to highlight kind of all these systems. This probably in total there are over 1 million calculations, and all of this was simply easily searchable, readable, and from there we're able to then much later in the future create a descriptor, a tool that uses the data that then can actually make predictions about experiments. Here the prediction is whether a material would be formed as a single phase, that is as a solid solution, or as multi-phase. based on this descriptor. And again, recently, this is related again to machine learning. So this is with Evazurg's group. So they came up with a way to create a machine learning, I guess you can say, interatomic potential to accurately calculate the convex hull. So the convex hull they got from AFLOW, which again, the AFLOW module for convex hull has been developed quite a long time ago. And very recently, we tried to move everything to machine readable, which allowed them to kind of quickly take our data, pass it through their workflow, and then produce a convex hull that is actually quite accurate. And then they even found some low energy structures that we did not originally catch in AFLOW. And the last thing is, this is, we're not really, we're not the authors on this paper, but this is kind of a new gigantic machine learning model kind of that was developed by Metas of, formerly Facebook. And why I bring this up is because if you remember all the way back, I showed you the kind of the way we label structures, the prototypes. So in fact, the database that they created was they just used our prototypes and just populated with whatever atoms they were interested in, and that their did their DFT calculations. So to summarize, AFLOW provides very again, high fidelity ab initio calculations and kind of a no-thrill storage. That's what it's really designed for, and that's what really, let's say works well for us. Again, 20 years of active development, so there's a lot of things that we learned that are maybe now very obvious, but back then maybe things did not exist or they're still in their infantile stage. And as of now, there's over 13 modules, and that's maybe one of the, and if you want to use one of the modules, you typically have to, let's say, already have been using, so you have to start, let's say, your calculations in AFLOW, because it analyzes the, let's say, the AFLOW workflow. So if you don't have this, let's say, if you're not using AFLOW, then you would not be able to, let's say, make use of the modules other than, let's say, recoding the module yourself for your workflow. So that's kind of one of the benefits, let's say, to maybe using it over AIDA, is that you would have access to these modules. And then I kind of went over the things that we learned and the recent uses of AFLOW. So with that, if we have any questions.
Okay, so since you introduced that you have pretty standard like compiling, unit test, everything, would the whole team be interested to cooperate with Julia Unity to run a Julia interface for that? Because we have binary viewers, we have client.jl, we have every tools that is ready to be used with any C++ libraries.
Yeah, that's definitely, we're definitely open to that. Like I quickly, I don't know if people, let me go all the way to the beginning. So one thing with the module, we do have a Python like interface, but yeah, creating also a Julia one, yeah, by all means. Of course, we also need people to, let's say we don't really have someone dedicated to just doing, let's say, AFLOW maintenance, but this is a task that we can split amongst the current group. So you can send us, I can give you my contact, or if you go on the AFLOW website, you can see all our emails. So email one of the postdoc, including myself. Yes. Jason.
Thanks for the talk. So I think over the 20 years, and you already encountered like many different bus version change. So how AFLOW manage this different bus version of like different output? You have any schema and how ways changed, how you manage this?
Oh yeah, it's that's a nightmare. It's a nightmare. We have a very big function that can figure out what version of VASP you're running currently and what version of VASP you ran your calculations with. And it can adapt to whatever, so all the way I think from version 3 point something to 6.1 or 2, that's the current version of VASP. So it's basically this gigantic function that can tease out what current VASP version you have, and it's really tough to read because you have to somehow be familiar with how the old VASP output looks like. So for me, like I've never seen how VASP 3 output looks like, so I'm assuming that part of the code is correct, but the fact that it was used probably means it was correct, and we've never had, let's say, false positives, or something where you ran on version 4, but it thinks it's version 6. So we've been, that's kind of what it is. It's this very big function that has a bunch of if statements that looks through the, let's say, the raw output of VASP.
Yeah, I have a quick question on the project development side. I noticed that your team is relatively smaller than AIDA's team, and it's purely in the academia setup. And I do notice that you also have the GPL's license. Is it intentional to like block the industrial contribution?
Industrial contribution? I don't think it was something that was done intentional. It might have been just simply an oversight because
GPL is super restrictive. As some industry partners, they have to quarantine their team members who read the GPL. Like even if you look at the code and they passively in your brain, and you can bring this idea into your own code. And another question is, I don't see I found the source code, but it's not posted anywhere.
Yeah, so that's something that we're trying to. So the source code should be on the AFLOW website.
Yeah.
So if you will have like the zip. So we're now trying to migrate to GitHub. It was like a big, let's say, internal discussion about moving things to GitHub. So with the latest version, technically it should be out before the end of the year.
Yeah,
it will be on GitHub.
Otherwise, you're missing the user inputs.
Yes. And that's why we're trying to push for that. A lot of there's a lot of old school people. So once they left and kind of the young blood came, I don't know if I'm offending anyone. I don't think so. We were able to convince, let's say, convince the group that we should be transitioning this way. Mm-hmm. Yes.
How does your Python wrapper work?
Good question. I mean, I'm not really. So I think it was under the hood. It is the C++ functions, and then you just simply import the.
Do you know which sort of strategy?
No, I was not involved. This was written way before me, so I don't before I joined the group, so I'm not really sure. But
Sure. The point was just, and I couldn't hear all the questions. Maybe someone else said this, but an easy starting point might be to wrap some of the C++ so that you can access the database from Julia. It's relatively straight.
You mean wrap the C++ in Python?
There are Julia packages that allow you to wrap around C++ code.
Oh, okay.
And in my biased assessment, it's sort of like of the various Python strategies, this is why I was asking how your Python wrapping works. Yeah. It's maybe slightly harder than the best Python strategy, but easier than most of the other Python strategies, so it's not too hard.
Okay, good. That's good to know. So maybe it's not as complicated as
All right, well, let's keep things moving for now, and again, we'll have a lot of time for discussion.